Welcome everyone. It's time to do another Leetcode problem, and today's problem is problem 322, coin change. And this is one of the problems in blind 75 list. So the problem description says that we are given an integer array coins, which represents that array represents different denominations of coins. And also we are given an integer amount, which represents the total amount of money. Okay. So we have to return the fewest number of coins that we need to make up the amount. If the amount of money cannot be made up by any combination of the coins, then we have to return -1. And we have to assume that we can use each of the coins infinite number of times. Okay, so very simply put, we can say, suppose you go to a shop and the shopkeeper is going to give you some change, and he has different kind of coins to use, and he wants to minimize the number of coins to give you back the change. So for example, in the first example, you can see that the amount is 11, and the type of coins that can be used is, say, 1 cent, 2 cent, and 5 cent. Okay, so obviously 11 can be broken down into 11 1 cent coins, right? Or it can be broken down to, say, 2 of the 5 cent coins, right? And 1 cent coin. So there are like 3 of them total, right? Or it can be, say, 11 can be broken down into 5 of the 2 cent coins, right? 5 coins, and then 1 cent coin, so total 6. So 6 here, 3 here, 11 here, right? So different ways we can do that. We have to find the minimum number of ways. So in this example, actually, this is going to be the minimum. There are other ways to do that. So we can say 1 5 cent coins and 3 2 cent coins, right? So 3 and 1 4. Okay, but this is going to be the minimum. For the second example, you can see that the amount is 3, and the type of coin that can be used is 2 cent coins. Now you cannot use 2 cent coins to make up 3, so that's why the output is 0 1 -1. And for the last example, you see the amount is 0 and the type of coin is 1. So to make up an amount of 0, actually we don't need any coins. So even if there are like hundreds of types of coins, even in that case, the answer would have been 0, because I need 0 coins to make up 0 amount. Okay, so next let's talk about how can we solve this problem. So looking at the problem, we have to track the remaining amount and the coins that we are allowed to use. So we can use 1 cent coin, 2 cent coin, and 5 cent coin. Okay, for the ease, let's keep track of the indices of these coins. So in the coins array, this has index 0, this is index 1, and this is index 2. So we can break this problem into 2 problems. So what if we use coin 1? So if we use coin 1, the problem becomes the remaining amount will be 10, and the coins still I can use is 1, 2, and 5, because in problem description said that we can use any coin infinite number of times. Or the other option is I don't use 1. So I don't use 1. The only options left for me are coins 2 and 5. Okay, so for the left problem, you see we can still use the coins from index from 1, index 0. For the right one, the index starts now at index 1. So I am allowed to use only the coins that start from index 1 up to the end. Yeah, and then in the left, you can see already we have used 1 coin, right? So 1 coin has already been used. Okay. Now you see that this problem is actually broken down into 2 subproblems, smaller subproblem of itself, right? So can we say that recurrence relation That means if a big problem is broken into smaller subproblems of itself, we can say that the problem can be solved recursively. So obviously this can be solved recursively. So let's say the problem is coin change, right? So the coin change problem amount is 11, and then index, say, if index starts from 0, right? Can we say if this is the problem definition, this is the result of this is minimum of this branch and this branch, right? Because the problem says find the minimum number of coins to make this change, right? To fill this change. So minimum of, on the left side, you see that already one coin has been used, and the problem becomes filling up amount 10 using the coins starting from index 0, right? And on the right side, the problem remains the same amount of change, but has to be filled up with the coins starting with index 1. Just for ease of understanding, this one says that I still can use coins 1, 2, 5. This is index 0, this is index 1, this is index 2, right? And this one says I still can use coins starting from index 1. Is it clear to you now that we are able to create a recurrence relation, right? So let's draw a decision tree. Okay, so as you can see, I have used drawn only the left branches. That means everywhere here I have used a 2-cent coin, right? So I have used a 2-cent coin here, and then another 2-cent coin here, another one here. So I kept on using these 2-cent coins. From the right side, if I go to any of the right side, that means I can no longer use this 2-cent coins. So I have to create the 11-cent using just the 5-cent coins. Okay, so now, since this is a recursive problem, let's find the base cases. Okay, so let's draw the right side thing from here. So the right side thing is going to be 5, and this one will have a left side. So this left side is going to be 5 cent used, and still I can use 5 cents. And this right side is going to be still 5, but I am running out of coins. Okay, now if you can see here, this is a failure case because I cannot make up a negative amount with whatever coin I have. And this is also a negative case. In this case, I have an amount left, but no coin left. So these are two failure cases. Now let's see a success case. So success case is I have been able to exhaust the whole amount using coins, right? So this is a success case. Okay. So let's talk about the success case. So success case is if the amount becomes 0, right? Amount becomes 0. So how many coins we need to make up an amount 0? So this is equals how many coins we need. So can we say that if the problem, coin change problem, is amount is 0 and whatever coin we have, right? 1, 2, 3, 4, the result is 0. I don't need any coins to make up a amount 0, right? Okay, so this is going to return 0. So this is going to return 0. But once it goes up here, already you see this is from the left. This comes from the left. So once it goes here, the problem here becomes minimum of 1 plus 0. That comes from the left. And then what is from the right? What is a failure case? So let's talk about the failure cases. Okay, so for failure cases, let's look at another thing here. So say the failure value is f, right? Okay, so once it goes here, it's going to be minimum of 1 plus this failure value and then from the right side, whatever we get, right? Whatever we get here. Now, as you can see, to make sure that this one takes a minimum, let's put a large value here, right? So the F value has to be large. So, and if I add 1 to F, I shouldn't get a value that overflows even my largest value. So what if we choose this value, integer dot max -1, right? Can we use this so that making sure that if I put it here, it's still by adding 1, it remains integer dot max, and I'm not overflowing anything. Okay, so that's another thing. So we found the 2 failure cases. We found what value we are going to send if I fail, right? So that's going to be integer. This large value that we are going to send is integer dot max -1. So let's keep on breaking down on the left side tree as well. So on the left, I will go left, and every time I'm using the 1 cent coin, and still I can use the coins starting from 1 cent. And from the, if I go to the right, I'm not using the coin, so the amount remains the same. So I keep on doing this, and let's draw a few more steps. So as you can see here, this tree is actually growing exponentially. So we have exponential number of states. So if we grow like this, then we'll need like exponential amount of time, and recursively trying to solve this may cause time limit exhaustion. But if you carefully look at it, you will see something interesting. So you can see that this one and this one is actually the same state. That means we can actually save the results of different states and calculate it just once. And if we have calculated it here, I will save the result somewhere and then immediately use it when this thing appears. Okay, so let's keep a memory for that. So to keep a memory, you can see that in any state we have 2 things. One is the amount, and then the second thing is the starting index, from which index I'm allowed to use the coins, right? Okay, so bringing it together, so where memory is going to be amount +1. The +1 is because the amount may go up to 0, right? So the amount is, let's say, 11. So I will take all the values from 0 up to 11, right? Okay. And this is the coin index. For this particular problem is going to be 0, 1, 2. So this is the amount up to 11. And the coin indices are going to be 0, 1, and 2, right? So 0 means that I can use all the coins 1, 2, and 5. 1 means if I am index 1, that means I can only use coins 2 and 5. And if I put like index 2, that means I can only use coin 5. Okay. So to make amount 0, right, how many coins I need? Given if I am given 3 coins or 2 coins or 1 coins, in all cases, I don't need any coin, right? So these are minus zeros, and let's initially fill all of these up with -1. Okay, okay. So let's see here. So here you can see 0 is being returned here, right? This one returns integer dot. So this part returns this, right? Okay. So this one is actually going to be memory of amount remaining is 5, and the index that the coin starts is 2, right? So that is going to be 1. That comes from here, right? Okay. So that means this one returns 1. And from this side, you can see I cannot actually make 1 cent using just 5-cent coins, right? So this is also going to return false. I cannot make 3-cent coins from 5-cent coins. I cannot make 7 cents using just 5 cents. I also cannot make 9 cents just using 5 cents. I also cannot make 11 cents just using 5 cents. Okay, so we can say that this is going to be integer dot max minus 1. What is the failure value was? Let's say if we call it like, so this is integer dot max, right? And once something has changed, a value has changed from, so this is the memory value for 2, and the index here is, this is index 2, right? So this is going to be this. And once this is no longer -1, we just keep on returning this. So I return this here, I return this here. And if I come here, you can see 1 is returned from here, and integer dot max is returned here. So the minimum of these two is going to be 1, and this is going to return 2, right? So this is going to return 2 because 1, this comes from the left side. So 2 and this large value. So this one will get 2. That 2 is going to be returned here as 3, right? So that's going to be returned here as 3. So that is going to be returned here as 4. So as you can see, and this one finally comes from the right side, so nothing is going to be added. So 4 is going to be returned here. Okay. Now let's look at from this perspective. Let's change this one. Say this one will come as 10, 5. So as you can see, this is going to return 2, right? And then we'll have something else from the left side, but that's more than 2. This 2 is going to be returned here. And then from this side, we'll have like more than 1 coin, right? We are using 1 cent and 2 cent. And then, but from the right side, so from left side, we are returning more. So 2 is going to be the minimum here. So 2, and then this one is from the left side, so we are going to return 3 here. Okay, so ultimately the result is going to be minimum of 3, or let's say, yeah, so 1 plus 2, 1 plus 2, and 4 from the right side. So it's going to be 3. So let's talk about the code. We have this cache value, and the 2-dimensional cache array. It has, for the row, we have amount plus 1 rows, number of rows, and the type of coins, that's the column, as I have shown you in the example, in the explanation. If the amount is 0, I don't no longer need to do anything. I just return 0. Otherwise, I fill up these whole 2-dimensional array with -1. And then I have this coin change overridden function where I put them remaining amount, the starting index. Okay, so let's look at this one first. So this is the helper function, the coin change helper function. It takes the remaining amount, the starting and the index of the coins that I can use, obviously the coins, and also the memory. Okay, the cache. So if at a certain point the remaining becomes 0, I return 0, or if the remaining goes negative, or I am running out of the coins, then I'm returning integer dot max value -1. I showed you in the explanation why. And since I am keeping like calculating every state just once, so if I calculate a state, that state will get a value assigned. It will no longer remain -1. We have initially filled up the memory with the cache with -1, right? So if it's no longer -1, that means that state has been calculated somewhere in the past. Instead of calculating it again, I just return the calculated value for that state. And then we have two options from each state. So if I'm at this point, that means this current state has not been calculated yet. This current state has this remaining amount, and this is the start index of the coins that I can use. Okay, so I can either use this coin in the starting index, or I may not use it. So if I use it, then the value is going to be 1. I use the coin, and then the next coin change problem becomes remaining. And since I have used the starting index coin, so the coin's value from the starting index, and for the next state, I still can use this coin, right? But if I don't use it, in that case, the remaining remains the same. And from the in the next state, I can just use the coins from the next starting index, right? Okay, so I got these two, and then I take the minimum of it, and assign it to the current state value, and finally return it. Okay. Okay, so this is the helper function. So in the main function, I call this helper function. Initially is the whole amount. The starting index is 0, and I get the result. And finally, what I have to check is if the result is still integer dot max value minus 1. If still that's the case, that then I know that there was no feasible solution. In that case, I have to return -1. Otherwise, I have to return the result. Okay, so that's what the program description said. Okay, so what's the time complexity of this algorithm? As you can see, we have, if this is the amount, so amount into number of coins. That's the space complexity, right? So that's the space complexity. That's clear. And what is the time complexity? So as you can see, we also have, like, how many states we have? These are different states, right? So every state has an amount, and also the starting index. So amount into starting index, that means the number of coins, right? So that many states we have, and for every state we are calculating just once. So if I'm calculating this, next time I'm not calculating this, I'm just using this result here, right? I'm using this result to return here. So that means every state is calculated once, and the number of states we have is amount into number of coins. So the time complexity is also the amount into number of coins. So that's it. Thank you very much for watching. We'll come back with another problem discussion next time.